Hello students, and welcome to this module of Home Tutors. In this module we will be looking at current electricity, and then briefly an outline of the different sections we will be looking at in this module are: we will be looking at the concepts and definitions as well as units that are used in current and electricity. We will be looking at electrical symbols. We will be looking at Ohm's law. We will be looking at resistor arrangements, parallel arrangements, series arrangements. We will be looking at resistivity, and then we will be looking at some important applications like Wheatstone bridge as well as the potentiometer. What you will notice conspicuously is that this particular module will be mainly focused on direct current. We have another module which is labeled Advanced Current Electricity, that deals with concepts of alternating currents as well as electromagnetic induction. So then we think we need to deal with DC first, and then I think I'm recommending this for you as a prerequisite before you try to get or listen to the advanced electricity module, which basically deals with issues like electromagnetic induction as well as alternating currents. Okay, so that taken, now we go ahead to concepts, definitions, and units that are used in electrical systems. The study of electricity is a very important topic because a whole lot of our technological world depends on some form of electrical power for effective functioning. For example, appliances such as the radio, television, computers, electric fans, etc. need electricity to operate. Before we undertake this crucial study, therefore, let us run through some definitions on which the study is hinged. Electric currents. An electric current I is defined as the rate of flow of charge around a circuit. An electric current symbolized with the alphabet I is the rate of flow of charge around a circuit. The quantity of charge Q is measured in the units called coulombs. Hence, from our definition for current, we can express it mathematically as current I is equal to quantity of charge divided by time. Remember, we said electric current is the rate of flow of charge around a circuit, that is quantity of charge per unit time. So symbolically, I equals to Q over T. Alright, so ideally, from our definition for current, its unit should therefore be the unit of charge divided by the unit of time, that is coulomb per second. But then this unit has been given a special name called the ampere with a unit of A. So therefore, current is symbolized by I and the unit of measurement is the ampere, also symbolized by A. But don't forget the definition. Current is the rate of flow of charge around a circuit. Therefore, from that definition, you can take note, especially for an objective kind of question, that the ampere is equivalent to a unit called coulomb per second. So another acceptable unit of current is the coulomb per second. Okay? Therefore, 1 coulomb per second is equal to 1 ampere. Example 1. If 8 coulombs of charge passes through a wire at a steady rate in 2 seconds, find the value of current passing through the wire. Simple. I equals to Q over T. Therefore, I equals to 8 over 2, which equals to 4 ampere. Some multiples of the ampere are defined as follows. We have the milliampere, which is 0.001 A, and then we have the microampere, which is 1 times 10 raised to the power minus 6 ampere. Current can be detected by the use of a sensitive instrument called galvanometer. Okay, take note of that. Galvanometer is an electrical instrument used in the detection of the flow of current. Current is measured with the use of an ammeter for large current or a milliammeter for small current. Take note that the galvanometer is used in detecting the flow of current, whereas the ammeter is used in measuring the quantity, the value of current. So the galvanometer does not measure the quantity of current, it only detects the flow of current. So take note of the difference, that the galvanometer detects the flow of current, but the ammeter measures the amount of current. Now let's talk about potential difference. Potential difference is a kind of electrical pressure difference between 2 points in an electric circuit. And when a current flows through a wire, it does so because there is a potential difference between those ends of the wire. So it is the potential difference between 2 points in a wire that drives the flow of current across the wire. Therefore, the potential difference PD between any 2 points in a circuit is the work done in moving 1 coulomb of charge between those 2 points in the circuit. Take note of this important definition of potential difference. It is a work done between any 2 points in a circuit in moving 1 coulomb of charge between those 2 points. The potential difference is measured in volts, symbolized with the alphabet V. And the instrument for measuring the potential difference across 2 points in a circuit is called the voltmeter. Alright, the voltmeter is used in measuring the potential difference between 2 points in a circuit. And the unit of potential difference is the volts. However, it is also noticed that cells, e.g. batteries, gives electrical force across their terminals. This force is called electromotive force, EMF. The EMF of a cell in volts is the potential difference between the terminals of the cell when it is not delivering any current to the circuit. Okay? That is, it is the potential difference, that is the amount of energy, power possessed by a cell that has no external load connected to it. Alright? Is the EMF of a cell in volts is the potential difference between the terminals of the cell when it is not delivering any current to the circuit. And then we'll also have multiples of potential difference. You can have the millivolts and then you can have the kilovolts. In mathematical expressions, potential difference is designated V, while electromotive force is designated E. Electromotive force is the potential difference of an open circuit. Alright? The potential difference possessed by a cell that has no load connected to it. Now let's talk a little bit about electrical resistance. In electricity, we often think in terms of the ability of a material to prevent the flow of current through it, and this is what is called resistance. The resistance of a material is its degree of opposition to the flow of current through it. A material is called a good conductor if it has very low resistance. That is, it allows current to pass easily through it. E.g., iron, water. Alright, they have low resistance and therefore they are called good conductors because they will allow electricity to pass through. While a material is called a poor conductor if it has a high resistance, e.g., wool, dry wood. An ideal insulator is a material with infinitely large resistance. Okay, so when a material has an infinitely large resistance to the flow of current, it is called an insulator. And such material, no current passes through them. E.g., we have special alloys like constantan, manganene, and nichrome. These special alloys are good insulators because they have infinitely large ability to resist the flow of current through them. In a circuit, any component which is specially designed to provide a known amount of resistance is called a resistor. Okay? Resistors can be those special alloys like manganene, constantan, nichrome, or any other material that has been designed to provide a known amount of resistance. Usually we have standard resistors, and these are resistors which have fixed resistance values. They are made by cutting up measured lengths of resistant materials like constantan and manganene and mounting them on a wooden block and providing them with terminals for connection. However, a resistor whose resistance can be varied is known as a variable resistor, and a special type of variable resistor is the rheostat. So we have the standard resistors, which are resistors with standard values of resistance. Okay? And then we have resistors whose resistance can be varied. Those are called variable resistor, and a very special type of variable resistor is the rheostat. In circuit calculations, resistance is designated R, and it is measured in units of ohms with this omega symbol as the symbol representing ohms. An electric circuit is an arrangement of electric sources and conducting parts through which a current can continuously flow. Like you can see here, an arrangement of electrical sources. Now, the electric source in this case is this cell, the battery. Okay, and here is the wire connecting the terminals of the battery. All right, so this now is the conducting path through which current can flow, and then this is the load where the current is converted into light. All right, so an electric circuit is an arrangement of electric sources, a battery in this case, and a conducting part through which a current can continuously flow. A simple circuit consists of a small light bulb, a battery, which is the source of the EMF, and two pieces of wire, which are conducting devices. The electric current flows from the negative terminal of the battery through one piece of connecting wire, through the bulb filaments, also a type of wire, through the other piece of wire, and then back to the positive terminal of the battery. So, when the electric current flows through the filament heats up, and then the bulb lights. Electric current can be detected by the use of very sensitive instruments called galvanometers. Remember, we said that earlier. Electric current can be detected with the use of galvanometers. However, for the measurement of the precise amount of current, we use an ammeter. All right? And then, depending on the sizes of the current we want to measure, we can either use milliammeters or microammeters for small amounts of current, while we use the standard ammeter for large values of current. Potential difference is measured with the use of an instrument called a voltmeter, while standard resistors carry the value of the resistance they offer to flow of current through them. In circuits, electrical instruments and quantities are represented with standard circuit symbols, some of which are, anytime you see a rectangular box like this, and usually a resistor diagram will carry as part of the diagram the amount, that is the quantity of resistance which it offers. In this case, it is C ohms. In terms of quantities, you can have a resistor labeled 4 ohms, 10 ohms, 1 ohm. Okay, this is the standard circuit symbol for a rheostat. Remember, we said the rheostat is a special kind of variable resistor. Okay, we have standard resistors and we have variable resistors whose resistance can be varied, and a special type of variable resistor is the rheostat. This is the ammeter with symbol A. This is the galvanometer for detecting the flow of current, ammeter for measuring the precise amount of current, capacitor, voltmeter, V, earthing, and then crosswire. So these are some electrical instruments and circuit symbols. Now let's talk about internal resistance. Remember earlier we said that even when a battery is on open circuit, there is still a potential difference across its terminals, known as the EMF. Okay, that is the maximum potential difference anyway that a battery possesses, a potential difference even when there is no load connected across its terminals. And this potential difference is actually as a result of the resistance of the electrolytes. The electrolyte, that is the conducting fluid between the terminals of the cell. Alright, usually cells contain liquids which are called electrolytes. These electrolytes themselves offer some form of resistance to current flow through the cell, and this resistance is what is called internal resistance of the cell. Therefore, it is noticed that the magnitude of the current delivered by a cell depends not only on the EMF but also on the value of the internal resistance. In circuits, internal resistance is designated by small r. Remember that resistance of the external load is designated by capital R, but the internal resistance of the cell caused by the resistance of the electrolytes in the cell is designated by small r and is usually shown as a resistor next to a cell. If the internal resistance is low, a large current is obtained from the battery, and vice versa. If the internal resistance is high, the current that will be obtained from the battery will be smaller. Now let's talk more about EMF. The EMF of a cell is defined as the potential difference between the terminals of a cell when it is not delivering any current in an external circuit. In a circuit, EMF is designated by E, and it is also measured in volts. Therefore, the EMF is the maximum potential difference that a cell is capable of providing, and it is equal to the sum of the PD across the loads within a circuit. Alright, remember we said that the internal resistance is designated by a resistor next to the cell. So this is a cell and this is a resistor next to the cell designated with the symbol small r. Remember we said that internal resistance is symbolized as small letter r. So this is the internal resistance of this cell, while these are the external resistances of the loads that the cell is supplying. Therefore, the EMF of this cell is given by V1 plus V2 plus V3 plus V. Alright, that is the potential difference across the resistor R plus the potential difference across the resistor 2 plus the potential difference across the resistor 3 plus the potential difference across its own internal systems, the potential difference across the electrolytes inside the cell. All right, so EMF of this cell is equal to V1 plus V2 plus V3 plus V. Now let's look at Ohm's law a little bit.